in terms of percentages then of the normal curve is that we would expect in the population approximately 68% of people would score somewhere between a 2.5 and a 3.5 if our standard deviation is 0.5. It's essentially saying on average people score a 3 plus or minus 0.5 points. And so notice that one standard deviation above or below the mean is a smaller gap of our sample relative to if we were including people or considering people who scored within 2 standard deviations above or below the mean. So as our standard deviations get larger, as those brackets get larger, we're including or describing, we're counting larger portions of the sample until eventually we're trying to estimate almost 100% of the population. So we expect that approximately 95% of the population will be within 2 standard deviations of the average. Likewise, we expect that 99%, approximately 99% of the population will score within 3 standard deviations of the mean. So I should also clarify, if one standard deviation is equal to 0.5, then that means 2 standard deviations is exactly 1 point above a mean of 3. And this is just an example. But so if we have an average of 3 and we calculate a standard deviation in our sample of 0.5, that means a person who scored 1 standard deviation above the mean scored 3.5. A person who scored 2 standard deviations above the mean scored a 4. Exactly 1 point or 0.5 twice above. So that means a person who scored 3 standard deviations above the mean would score 1.5 points above 3, the average, which means they originally scored a 4.5 because 3 plus 1.5 is 4.5. And so that's how you interpret individual scores along this continuum of standard deviation units. So here are some cumulative percentages then that tell us approximately if the normal curve is accurate, how many people should score above or below a certain point in the distribution. And so when data are normally distributed, that means that 50% of the sample should score average or below. So along the bottom here, under the standard deviations in the distribution, you can also see that we would expect less than 0.1% of the population to exist beyond 3 standard deviations from the mean. That's true when you look at 3 standard deviations below the mean. That's also true when you look at this portion that is 3 standard deviations or more above the mean. You see that 99.9% of people should score lower than 3 standard deviations above the mean, which means that only 0.1% of people should be that high in whatever construct you're measuring. And so you can look at each of these percentage marks. I put these here because it kind of segues into a nice example that you're probably more familiar with. So you might be familiar with percentile scores from standardized testing that you've done in the past. And these scores are very similar to z-scores in that they tell you how an individual scored relative to everyone else. For example, if you find that you score in the 84th percentile on a test, and per this normal curve here, you are exactly 1 standard deviation above average, which estimates that you rank higher than 84% of the population. In other words, 84% of the population are below you on this spectrum. So the takeaway here is as the standard deviation gets higher, so I should say not necessarily larger, but higher in terms, it becomes more positive, like positive 1, positive 2, positive 3. Percentile rank is getting higher, meaning that fewer and fewer people exist in that interval of the distribution. Likewise, as the standard deviation becomes more negative, so farther and farther below the mean, the percentile rank is getting smaller and smaller, still indicating that fewer and fewer people exist in that portion of the distribution as well. Most people fall somewhere within 1 standard deviation.